Now we have seen all the classical approximate methods. That is, the first method which we had seen was a variational method, and the second method which we had seen was weighted residual method. And in variational method, the method which we'll be using constantly along with the FEM is Rayleigh-Ritz, and then from weighted residual, the method which we'll be using constantly for this finite element modeling is Galerkin's method. And then we had seen that now on, when we say Galerkin's method, it will be nothing but modified Galerkin method. So in this session now we'll try to see how this FEM is related to this classical approximate method, and then what are the basic difference between this finite element method and this classical approximate method which we had seen earlier. Now, one of the key steps in any approximate method or in finite element method is to choose an approximate solution right in the beginning. So in that case, so our step one would be always to select a trial function, and right in this step the difference between classical approximate method and FEM starts. For example, now we have here this problem, and our domain here is from 0 to 1. So our domain here is from 0 to 1. Our domain here is from 0 to 1, right? And then if I'm choosing the trial function, our trial function would have been u of x equal to a naught plus a1 x plus a2 x square in case of classical approximate methods, any of the classical approximate methods. And this trial function would have been applicable to the whole domain. It would have been applicable to the entire whole domain. In case if we were using still this classical approximate method, this chosen trial function would have been applicable to the entire domain right from 0 to 1. If you remember, our weighted residual definition was weighting function multiplied by residue over the entire domain was 0. Or if you remember this, variational method, our equivalent functional I would have been over the entire domain. So whatever we were choosing this trial function, that was applicable to the entire domain. But here in finite element method, what we will do is this entire domain from 0 to 1, we will divide them into small parts. We'll divide them into very small parts, Now these are the smaller parts, some large finite number of parts. And then let me call these smaller parts which are seen here, let me give them a specific name. So these smaller parts of this entire domain in finite element method, smaller parts are called as elements. As we had seen in the introductory video, the smaller parts of the domains are called as elements. And finite element method in universities revolves around finding the properties of these elements. The properties, when I say properties, it means stiffness matrix and mass matrix of these elements. So these smaller parts are called as elements. And now these points which I have marked in yellow, these points which connects the two adjacent elements, they are called as nodes. So these points are called as nodes, and these small parts are called as elements. So if I just want to number these elements, I will call them as this as 1, this as 2, this as 3. Let me call this as the mth element. This will be m minus 1th element, this will be m minus 2 element, and so on. Fine. So we have here total number of elements as m, and these points are called as the points which connects these elements are called as nodes. And then if I start numbering these nodes from here, this will be first element, this will be the first node, this will be the second node, this will be the third node, this will be the fourth node, and so on. The last node I will call it as n. This node will be n minus 1, this node will be n minus 2, and so on. So we have here n number of nodes and m number of elements. And then let me tell you now the basic difference between the finite element method and this classical approximate technique. The first difference is the approximate solution which we were selecting in case of classical approximate method was applicable over the entire domain the way we had seen it here. But in case of finite element method, and then since it was applicable in the classical approximate method, since it was applicable over the entire domain, usually the demand here was more. We had to choose a higher degree polynomial, say a cube x, a3x cube, or up to a4x to the power 4. We had seen that as we were increasing this number of unknown parameters, or we were increasing the degree of this polynomial, the solution would have was the solution was improving in case of classical approximate method. But here in case of finite element method, this won't be the case. We will be dividing this entire domain into small elements, and whatever is the trial function, we will define it over each element. So if I consider here one typical element, if I consider one typical element here, this is one typical element. I have considered it from this total number of elements. I have just considered here one element, and I have here two nodes, and let me name those nodes as node I and node J. These are my node I and node J. And the coordinates from this, if I look at the coordinates, this is nothing but, this is the point where x is equal to 0, and this is the point where x is equal to 1. So if I choose some coordinate to some element, so I will call this as x at node I, and this will be my x at node J. So these are my coordinates, and these are my node numbers. So in this case, in finite element method, when we'll be considering the trial function, it will be not be applicable to the entire domain as such, but it will be applicable to each element. And further, if I want to find the solution for this entire domain, we will combine the solution of this each element to find the solution over this entire domain. So this is the basic difference between the finite element method and classical approximate technique. So this is my typical element here, and let me call this length of this element as, say, LE. Again, in finite element method, the length of these elements need not be equal, or it need not be unequal also. It totally depends upon us. For example, if something exciting is happening at the boundaries, then of course I can choose the number of elements more towards the boundaries, and if nothing interesting is happening in between, I can choose a comparatively larger length elements, and so on. That you will understand it in a while. But there is no rule as such that all the lengths should be equal. It can be of any lengths, it may be even unequal lengths. It is totally up to us. But the first difference between the classical approximate method and finite element method is that in classical approximate method, the trial function was applicable over the entire domain, but in case of finite element method, the trial function is applicable only to each domain. And that is why, to improve this approximate solution in case of approximate method, we had to usually choose a large degree of polynomial. But here, since it is applicable only to the small element, the degree of polynomial can be reduced. And then here, if I want to improve the solution, then I will have to consider the more number of elements, and we can still stick to this linear polynomial function. So this is the basic difference. So here in this case, this m stands for m stands for number of elements. These are very important terms. N stands for number of nodes, number of nodes. Then this I comma j stands for node numbers. I comma j stands for node numbers. For example, if I'm picking up the node from if I, for example, if I'm picking up this third element, then this I will be 3 and j will be 4. If I'm picking the element from here, then this I will be 2 and j will be 3, and so on. Xi and xj are the coordinates. Xi and xj are the coordinates. Xi and xj are the coordinates. To be more specific, they are Cartesian coordinates. Le is the length of this element. Le is the length of this element. So these are the basic terms which we need to understand. So this is the first difference between finite element method and classical approximate method. The second difference is again, it lies in this approximate solution itself. In case of classical approximate method, we were choosing the trial function in such a way that it had some unknown parameters like a0, a1, and these parameters had no physical meaning, no physical meaning as such, they were just some mathematical unknown quantities, right? In case of approximate method, they were just some mathematical unknown quantities, and upon finding the values of those unknown mathematical quantities, we were substituting them back in the admissible trial solution, and that was our solution over the entire domain. But in case of finite element method, one of the basic concepts, in fact, of finite element formulation is this trial solution is expressed in terms of unknown solutions at the nodes. That means here this u of x is the solution of this element, but if I want to find what is the solution at node I, then that will be ui, and at node j the solution will be uj. That means ui will be the solution at node I, and uj will be the solution at node j. So this, in case of finite element method, we will try to replace this mathematical unknown parameters in terms of solutions at the nodes, so that when we get this by the finite element method, when we obtain the values of this unknown parameters, it will be directly the solution at the nodes of this elements. And that is why in finite element method we get solutions at the nodes and not anywhere in between. So hence it is always advisable in finite element method that if you want a greater accuracy, we need to do the fine meshing or discretization, so that we have more number of nodes and we will get the solution at more number of points. This is the second difference between the finite element method and the classical approximate method. This is the second difference, that in finite element method these unknown parameters are replaced with unknowns at the nodes. And how exactly it happens is, from this element diagram, we have at x equal to xi, we have the solution u as ui, right? And at x equal to xj, that is at this node, at this coordinate, we have u as uj. So if I substitute this here, that is u at xi, we have ui, that is a0 plus a1 xi, and then at x equal to xj, we have u as uj. So this will become a0 plus a1 xj. Now if I solve these two equations simultaneously, I will get this a1 as a1 equal to uj minus ui divided by xj minus xi. And similarly, if I find the value of a naught, I will get this value of a naught as ui minus uj minus ui divided by xj minus xi times xi. And then further, if I simplify this, I will get this as ui times xj minus uj times xi divided by xj minus xi. But this xj minus xi is nothing but the length of this element. For example, suppose say this coordinate is 0.3 and this coordinate is 0.5 from this domain, then the length of this element will be 0.5 minus 0.3, that is 0.2. So this is exactly what will be done here. So further, this xj minus xi will be nothing but the length of that element. So a1 can be given as uj minus ui divided by le, and this will be given as ui xj minus uj xi divided by le. So we have been able to find the value of these constants a naught and a1. If I substitute them back here, a naught is nothing but ui xj minus uj xi divided by le. Then we have plus a1, we have got it as uj minus ui by le times x. Now I need to do some mathematical manipulation, some readjustment, because I want this a naught and a1 as ui and uj. So that is what is approximate solution in finite element method. In place of unknown parameters, we have the unknowns as a solution at the nodes ui and uj. So if I do that, I will get it as xj minus x divided by le times ui plus x minus xi divided by le times uj. And this quantities xj minus x divided by le can be called as xj minus x by le can be called as ni, and nj can be called as x minus xi by le, and these quantities are called as shape functions. A very important term in finite element method. And in fact, this is the one way of deriving the shape functions. The other method by which the shape function can be derived is a Lagrange's interpolation function, which we will be seeing in the later topics. But for time being, you consider this as the way of deriving the shape function, a very important concept in case of finite element method. So finally, I can write this solution as ui ni plus uj nj, and this will be our trial function in case of finite element method. So what we have done basically is we have replaced these unknown mathematical parameters which had absolutely no physical meaning with that of the unknowns at the nodes. So this ui and uj are the unknowns or the solutions at the nodes. So when we will be determining this ui and uj by finite element method, we will directly get these values of the we will directly get this values of this element at its nodes. But what about the values in between? We discussed that the finite element method will give us values only at the nodes. But what if I want to find the value somewhere in between? And that is when exactly this shape functions will help us. For example, this shape function contains the x coordinate. X is nothing but some general distance from this point. So if I want to calculate the value at say at this point, at this x, because finite element will be giving us the solution only at the nodes, but if I want to find the solution somewhere here which is at a distance of x from here, I can only substitute. What I can do is in this trial function I can just substitute the value of that x. I can just substitute the value of that x, and then uy and uj will be the values which will be determining from the finite element methods. Le is the length of the element which will be knowing. Xj and xi are the coordinates of this element. So basically what I'm trying to say here is the finite element method will give us values only at the nodes x at ith node and jth node. But if I know the shape functions, or these functions are also called as interpolation function, what they will do is it will interpolate the result by taking the values of the nodes I and j, or by taking the nodal values it will interpolate the result using this interpolation function. These shape functions are also called as interpolation function. It will interpolate the result and it will give me the result or the solution at any value of x. But let me remind you again, those will be only the interpolated results from the nodal results. So this is the second major difference between the classical approximate method and finite element method. All these differences I have listed down here. You can go through them again. So let us see now some properties of these properties of shape function, properties of shape functions. These shape functions are also called as interpolation functions. These shape functions are also called as interpolation functions. So we have seen that ni, that is the first shape function here, is given as xj minus x by le, and nj is given as x minus xi by le. Now the first property of this shape function is the sum of this shape function will be always equal to 1. Sum of shape function will be equal to 1 or unity, and that you can check here. So ni plus nj will be equal to xi minus x plus x minus xi x sorry, this should be xj, so divided by le, and this will give us xj minus xi by le, and xj minus xi is nothing but again the length of the element le, so this will become le by le, and that will become 1. So the sum of the shape function will be always equal to 1. This is the first property of shape function. The second property is the sum of the derivatives of this shape function will be always equal to 0. So the sum of derivatives of shape function will be equal to 0. Now if I take the derivative of this shape function with respect to x, I will get the value of d and I by dx will be equal to -1, and d and j by dx will be equal to +1, and then if I add them up I will get it as 0. So the sum of derivative of shape function will be always equal to 0. This is the second property. And the third and the most important property of this shape function is the shape function ni will be equal to 1 at the ith node, and ni will be equal to 0 at jth node, and similarly nj will be equal to 1 at jth node, and nj will be equal to 0 at ith node. That means these shape functions are equal to 1 at its node. So ni will be equal to 1 here, whereas here it will be 0, and nj will be equal to 1 here, and here it will be 0, and that is very easy to understand also. So at ith node x will be equal to xi. At ith node ith node x will be equal to xi, and if I substitute that x as xi, this will become xj minus xi by le, so le by le will become 1. So at x equal to xi, that is at ith node, ni will be equal to 1 and ni will be 0 at jth node. At jth node x will be equal to xj. Jth node x will be equal to xj, because if you remember, our element was this was our ith node, this was our jth node, the coordinate here was xi, the coordinate here was xj, right? So at jth node x is xj, so if I substitute here xj, x as xj, I get ni as 0. So let me draw the variation of this ni. So this ni will be equal to 1 here at x equal to xj, and it will be 0 here at jth node. So this will be the variation of ni. It should be a linear variation, so let me draw it properly. So this will be the variation of ni. So here let me write this as ni. So this shape function ni will be equal to 1. The value of this will be equal to 1 at x equal to xi, whereas it will be 0 at x equal to xj. So it is 1 at its node and it will be 0 at the other node. Similarly nj will be 1 at x equal to xj, or at the jth node. So here nj will be equal to 1 and here it will be 0. So if I just draw it with a straight line, it will be somewhat like this, and this will be our nj, and this value will be again 1. So this is again a very important property, and if you see the variation of these elements, variation of the shape function, it is linear, because here if you remember, we had considered our solution to be a linear solution initially, so they will vary also linearly. So this is the third most important property of the shape function. So these are the three important properties of this shape function. Now one more important thing which we need to discuss regarding these shape functions, and that is in case of Galerkin's method or in case of modified Galerkin method. So from here on, whenever I say Galerkin's method, I address it I'm addressing it to the modified Galerkin method. In case of Galerkin method, if you remember, our weighting function was nothing but du by dai. This was our weighting function, right? If u was a0 plus a1x plus a2x square and so on, weighting function was the derivative of the approximate trial function with respect to its unknown parameters. But in case of finite element method, our trial function has become this: u is equal to ui ni plus uj nj. Now in this case, our weighting, in case of Galerkin's method, our weighting function will be wi will be dou u by dou ui, and that will be ni, and wj will be dou u by dou uj, and that will be nj. So in case of Galerkin's method, now the weighting function will be nothing but the shape functions itself in case of Galerkin method. And again, this is a very important concept which we'll be using at the later stages to solve the problems. That is, in case of Galerkin's method, in finite element method, when we'll be taking the help of Galerkin method, our weighting function will be nothing but the shape functions at that node. So wi will be ni and wj will be nj.